At this point, you've heard me talk a lot about how the sophisticated way to think about a matrix is to view it as a teleportation device in some sense. We can view an n by n matrix as a machine that takes vectors in R to the number of columns and sort of transforms that vector into a new vector in R to the number of rows. But we haven't said quite a lot about why we might want to do something like that. And a prime example here is the notion of a vector projection. So let's jump right in. I want to start here by just thinking about the motivation of why we might want to do something like this, or what it even looks like. I want to start with a question. And that question is, what is the projection, which I'm going to denote by PV, of some vector v in 3 dimensions onto the z-axis? So I want you to think about this problem in your head for a moment before we say what I think this should mean. So we're asking, what is the projection of this vector v in 3 dimensions here that we see onto the z-axis? So normally I pose this question to the class if we're hanging out together. And I've heard a lot of really good answers from students over the years. I'll often hear a student say, oh, well, the projection is some sort of shadow of the vector that is on the z-axis, which I think is a great way to think about it. But my favorite ever is a student one time said, oh, well, that's what we get if we just smush v onto the z-axis. And I love that language. It's very informal and non-technical, but it's visceral, and it makes a lot of sense, I think, geometrically. So that's how I think of it. If I want to project this vector v onto the z-axis, I want to somehow take v and smush it onto the z-axis. So the question now is, well, how does that even work mathematically? Well, mathematically, the way we might do this is we might go to the tip of v and draw an orthogonal ray onto the z-axis. And this gives us a natural way to think about what it would mean to smush v onto the z-axis. We could draw a vector starting from where v starts and then pointing where this orthogonal ray hits the z-axis. So that's our projection here, p times v. And if we think in terms of coordinates, I think we might be able to sort this out. What are we doing when we're accomplishing this? Well, if I'm taking my vector v, whose coordinates are v1, v2, and v3, what I'm really doing when I'm projecting onto the z-axis is I'm sort of just forgetting about the x and y coordinates and only preserving the z coordinate. That's to say, when I project v1, v2, v3 onto the z-axis, I'm producing the vector 0, 0, v3. And the thing that I want to point out here is that once we identify this on the level of coordinates, we realize that we can accomplish this with a matrix. So this projection is obtained with multiplication by a matrix P. Well, what is that matrix? That matrix is the identity matrix with the first 2 ones on the diagonal zeroed out. When I take this matrix P and multiply by v1, v2, v3, I produce 0, 0, v3, which is the projection of v onto the z-axis. So here we have a simple situation where we're trying to sort out in our heads what a projection might look like in some situation like this, and what do the numbers look like if I actually try to do it. Let's look at a different example. So here we have the same vector, but now I don't want to project onto the z-axis. I want to project onto the xy plane. So normally I would ask the class, well, what do you think that should mean? And people would say various interesting things. So maybe if I shined a light down from v onto the xy plane, that would cast some sort of shadow onto the xy plane, and that would be the projection. I love that language. I think that language is fantastic. But again, when I'm thinking of it, I have to confess, I'm just thinking about, well, I'm just going to take v and somehow squish it onto the xy plane. So again, mathematically, how would that work? Well, we apply the same principle we just did when we projected onto the z-axis. I'm going to drop an orthogonal ray from the tip of v down to the xy plane. And this gives me a location that I can draw a vector to. I can start at the origin here and then draw a vector out to where that orthogonal ray meets the xy plane. And that's my projection of this vector onto the xy plane. And again, if we think about the coordinates in this situation, I think we can sort them out. If our vector has coordinates v1, v2, v3, what does the projection look like? Well, we're not. What we're doing here is we're sort of forgetting about the z coordinate, and we're preserving the x and y coordinates. So the projection here should equal v1, v2, 0. And once again, I'd like to point out that this process is obtained by multiplying by some matrix P. What's the matrix P in this situation? Well, the matrix P that transforms a vector v1, v2, v3 into a vector v1, v2, 0 is almost the identity matrix, but here we're going to look at the identity matrix with the third one on the diagonal zeroed out. When I take this P and multiply by v1, v2, v3, I produce the vector v1, v2, 0. So that's sort of what I like to think of as the geometric motivation for doing such a thing. When we project a vector onto some space, what we're doing is we're sort of smushing that vector onto the space, and mechanically what that means is we drop an orthogonal ray from the tip of that vector onto the space, and that defines some vector that lives in the space we care about.